All right. Thanks so much for being here, and thanks so much for having me. So this is not really a hardware topic per se yet, unless buildings qualify as hardware too. But let's talk a bit about them. So we have exchanged buildings for a long time as just like sets of line drawings without really computer-readable semantics associated to them. I don't know, maybe there's a parallel to how, I don't know, the PCB community exchange models. But I don't know, I would say for the last 10 years or so, we're more and more exchanging buildings as rich, semantic data models, where the models we exchange have also a meaning that computers can relate to. And so in 2011, I started IfcOpenShell, which is a software library for dealing with these kind of models. IFC is the open standard. It's called IFC. It's called industry foundation classes, which is kind of a meaningless name, but that's where the name comes from. IfcOpenShell is one of the geometrical forms you can use to exchange representations of your building elements. IFC is also very much inspired by STEP, which is probably a standard familiar to most of you. So if you're familiar with STEP, you know OpenShell. And in IFC, we just prefixed everything with IFC. And then right there at some point, you see that there is, well, I wouldn't call it a spike. It's really like, I don't know, a mountain ridge of new contributors that came on board, and that's with the Blender BIM add-on. So in my work, I'm mostly focused on analysis of these kind of models. And then, Dion Molt came on board, and he started actually writing an authoring tool on top of IfcOpenShell that allowed people to really graphically create models. And, you can see the effect of that in terms of contributors. So we have quite a bit of modules, but in essence, we have a parsing library, geometry interpretation, so that we use predominantly OpenCASCADE, hopefully familiar to some of the people in the room, to read these kind of geometry definitions and translate them to BREPs, and then interact with them in a bunch of ways, convert them to tessellated formats, or some other things. So I started my module mostly in C++. The Python has been hovering around 0 for quite some years. And that basically had to do with the ecosystem. So OpenCASCADE is C++. It doesn't leave you much of a choice. But quite soon on, we realized that if you really want a wider movement, a richer ecosystem connecting different modules, but also that the BIM world is rather academic. So we have quite a bit of students or software developers doing rapid prototyping. So it really made a lot of sense to have an interpreted language with a more accessible syntax. So also quite early on, we started having Python bindings. And then, you see the same spike here, basically, in terms of contributors. The Blender BIM add-on is built on top of Blender, you might have guessed. And Blender is also obviously a wonderful piece of software, very extensible. And also, the client-side code is mostly in Python. But it's not only that, it's also really a higher level API that was being built on top of the low level, let's say, instance manipulation we had. IFC is really an extensive schema. It's roughly 1,000 to 2,000 classes or data types. And if you really want to interact with that in a meaningful way, you need to operate on a bit of a higher level. And that's also where that steep increase in Python code is coming from. But what my topic for today is really the geometrical challenges that I encounter. Because our industry is really multidisciplinary. So for example, what we exchange as building models are really detailed decompositions of the building into very specific elements. So one wall, one ceiling plate, and all the kind of supporting structure. But if you look at the building code people, this is from the city of New York, for example, they want to ask questions on much higher abstract levels, such as the facade. So it's New York. So they envision there is something like a base on top of which a tower is built. And there are requirements about the proportion regarding base and tower. But none of these things exist in BIM models. We don't even have a facade. We just have this bag of elements. But we have other, let's say, different perspectives on geometry. If you want to do thermal simulation, so we are here in this room generating a lot of heat, and that heat dissipates to neighboring spaces. And then you're also not really interested in all the detailed elements that make up your building. You just want to have basically a graph of spaces and thermal interfaces between them. And there are ways to exchange this information as part of IFC building models, but the generation of them is still rather buggy. And that's also the challenge, of course. Does every authoring tool need to implement this kind of generation of data? Or are we going to opt for a more collaborative ecosystem of tools, where you just generate a building model and there is other tools to enrich those models? And that is what I'm really hoping for, but it's not what we're currently seeing in the industry yet. Geospatial people, they really want to focus on the things you can see. They come from GIS, so they can only observe what is actually visible to them. So they don't really want to deal with this kind of invisible surfaces. They just want to have manifold representations of interior or exterior shells. But so this is what we have as a building model. And as a summary, what we want to generate, for example, is this representation of just the facade that joins across these walls. And it could be thousands of wall elements. The further you are in your development process of the building, the more you're going to decompose these things into the actual physical things that are going to exist in reality. But the data comes from heterogeneous sources. I really want to advocate for an ecosystem because we already have an open standard. Let's have a more collaborative ecosystem where we can augment this data. Here, the interior, where you really want to know, for example, will I bump my head here? But in normal models, these kind of representations don't exist. You don't have this higher level representation of the interior. You might have a description of the space, but it wouldn't be enriched with all the geometries that further eat out of that volume. And of course, none of this is ultimately very precise. So there is gaps either accumulated due to floating point rounding errors or manual sloppiness, or also on purpose. If you're building a building, you have to accommodate for the fact that the walls, especially if it's metal, they are expanding and contracting depending on the temperature. So there are also actual gaps between these elements in reality in more detailed models. So maybe that representation that I just showed of the facade doesn't in reality really exist as a volume. And then, so how to solve that? naively you would maybe think, yeah, let's just Boolean union these things together and call it a day. But yeah, that's quite a challenge in terms of performance. But you also have to make a choice there. Are you going to rely on these kind of fuzzy Boolean operations that allow for a certain imprecision, or still join these disjoint volumes, even if there is a nanometer or millimeter gap between them? Or that's the OpenCASCADE paradigm, for example. Or are you going to rely on these kind of exact Boolean operations that, for example, CGAL offers? CGAL has a very interesting number type, I think, where a number is just not just a number. It's basically a binary tree of all the operations that were used to construct a number. And as such, it is really arbitrarily precise. There is never any rounding occurring. But it obviously has a monumental performance impact. And it's also not maybe necessarily what you want, because you want to join across these kind of imprecision issues. So earlier attempts, they made the performance problem even more extreme by using a Minkowski sum. So you have kind of a padding volume that you apply to every element, enlarge it slightly, and then union them together, and then shrink. But this is not really feasible on detailed models. So what I try to do for this particular problem, and I hope this is going to end up I'm showing mostly experiments, but I hope that this will really at some point also be part of, let's say, the core parts of my software library. But what I'm doing here, for example, is decomposing these solid volumes into trees of half spaces, and then the neighboring half spaces average these out. So the two faces here, and here of these two disjoint walls, they are merged or aligned. And same here and same here. So this really allows for some sort of local adjustments so that you're really sure that things snap into place. And also, it really causes very neat models because there is almost no intermediate vertices, because all the nearly coplanar surfaces were exactly aligned. But this is still a challenge to make this work on the really detailed models. Another example where I used half spaces is if, for example, the facility management people, they also operate on a much higher level. They don't care about every rentable unit. They want to have aggregates of those. How many square meters of rentable space do I have across these models? And these interior partitions, you don't really care about them because tenants can remove them anyway. So you include them in your square meter counts, which means that you basically need to take this volume and extend it to this volume for them to touch, and then union these together. So for that, I used Sparkle, RDF-lib in Python. I built, this is what you see here is a graph of spaces, the volumes, the half spaces bounding the spaces. These are touching the faces of the wall, and in the wall you have an opposite. And so we really form a graph, and then I query that graph based also on semantics, so it's only the non-load-bearing walls that I can aggregate over. And as such, this kind of patchwork blanket is all the individual spaces that are in a model like this. And then what the facility management people want to know is this. So this is all inhabitable spaces, I think. So without utilities or these kind of things. But yeah, there are large performance problems still with these kind of approaches. This arbitrarily precise operations in CGAL, it's really immensely robust. The first, I really come from, let's say, I've 10 years of working experience with OpenCASCADE, so you come to lower your expectations a bit in terms of what works, how many crashes do you encounter when you load complex models. And then in CGAL, everything just works. It's not always what you want, but that is then your own fault, typically. But still really computationally intensive. So as a side project, I've also written my own voxelization library. Because especially these kind of challenges, superimposing a lot of elements into the same domain, closing certain minimal gaps, that's really what voxelization is perfect for. And so maybe if you would want to union all these kind of building elements in OpenCASCADE, it just wouldn't work. It's not robust enough. In CGAL, it will take a considerable amount of time. And in voxelization, it's really just, I wouldn't call it instant. You have to deal with a different set of challenges. Suddenly the complexity is no longer based on, let's say, vertex and face counts, but it's really based on the physical dimensions of your building. So if you're building a larger building, your computation takes longer. But it's still, it does perform better than CGAL, I would say. And then you can do topological queries on those again. So this is a very famous testing model that we use in our industry, but I expect it's a little bit cryptic for you to read. But let's say this is the exterior space, and here is a door, here is a door, here is a door, here is a door. Here you see a little bit of a stairway. So it's really three-dimensional, but I've kind of folded every 3D volume. I flatten it over the z-axis to kind of get a 3D volumetric voxel grid of just, let's say the mass that we can walk on. And then you can just do topological queries again on those to see how long is the evacuation distance from a particular point in time. And I'm not saying it's not possible on, let's say, regular polyhedra or BREPs. People have been doing that. But I came to really appreciate how trivial those kind of operations are on voxel grids. Same for the headroom, basically. It's the same kind of idea where I start from the 3D volumetric space interior that we can breathe in. I flatten that over the z-axis to just the little surface where we can stand on. But I remember how many voxels I've flattened downwards, and based on some sort of color coding or threshold, that's either sufficient or not. So you can see here under the stair that there is obviously a little bit less space to stand. So for this, these kind of when we started this project, we envisioned that end users would be writing their own kind of analysis scripts. So it's here you see the visually all the operations that were involved in one of these I don't remember which one, but one of these computation graphs to union those voxels, subtract a bunch of things, do these traversals, to really figure out the space where we can stand. We also do some sort of padding so that we don't start walking in like 2 centimeter areas where we kind of assume that we have a little bit of a body, so all the obstacles are dilated a bit. Some of these things are also element specific, so we do specific things with the railings. I don't remember the details, but we really created our own little scripting library for these kind of things. I don't remember why we just didn't create Python bindings. That seems like it's easier than really creating your own language with your own interpreter. But at that time, that's what I did for some reason. Yeah, and obviously nobody has ever tried to create their own little analysis script to do these kind of things. But yeah, as you can imagine, it also requires some documentation and stuff that we also didn't provide. But it was really fun to work on. Yeah, well, what I see as the advantages of this kind of voxelization, you can also associate numbers to the cells. So what you see in the headroom analysis, where you can stand, and the evacuation analysis, you can really associate a number with every cell. It's also in a uniform way across every dimension. That's also a bit harder on polyhedra, I think. Yeah, Boolean operations are really just that, Boolean operations. If you superimpose 2 cells, a 1 and a 1 becomes a 1, a 1 and a 0 becomes a 1. It's, yeah, that was really, if I can implement Boolean operations, then it's trivial. And yeah, it's efficient to calculate distances also, and we close these gaps. So yeah, I think for our built environment sector, it's really quite a good match even for some analysis. Yeah, so IfcOpenShell, going back to where it all started for me, it's quite an extensive software library. It has all the different revisions of the IFC schema. It has these geometry mapping functions. There's about, let's say, 200 classes in IFC that somehow affect geometry or representation. So yeah, they have an implication on our BREP conversion to OpenCASCADE. So they have these kind of conversion functions. And then, yeah, we rely on OpenCASCADE. But there is, yeah, it has gotten quite a large code base. And in the new version, I have been playing, well, it has been happening for various years now, so I shouldn't call it playing anymore. But let's say working on the idea to support multiple geometry libraries, because the robustness of OpenCASCADE has really improved dramatically over the past 12 years. It's really a usable, very powerful software library now. But there are still cases, if there's issues being reported on my GitHub, where I have to say, this takes me 2 months of investigation. I'm sorry, I just cannot help you with this. And in that sense, I have some hope. If I have a secondary geometry implementation in CGAL, then I can really provide the best of both worlds. Also to people that want to do this kind of analysis that I just showed earlier, like aligning these half spaces. They have a better starting point with CGAL. But for that, I created my own taxonomy in the middle of geometrical concepts, so that this kind of implementation here is a little bit easier. So what I've learned in all of this, so CGAL is predominantly only polyhedra. They have some sort of curved things in some packages hidden somewhere, but mostly polyhedra. The exact rational number type I've talked about. They have an interval that wraps them for performance. They have good documentation, but I find their set of packages somewhat incoherent and chaotic. You don't always know where you need to look, and it's not always easy to go from one package to the other. And I think the focus is rather academic. A lot of the CAD concepts that maybe we rely on, they don't necessarily offer out of the box. And that, maybe you can read for yourself what I think about OpenCASCADE. And that's it for me today. Thank you so much.
Okay, do we have any questions?
Yes.
Do you see any use for the CGAL library to help with the open cascade geometry? You would be able to use some of the functionality and get that back somehow to the output produced with thinking about FreeCAD and how this could be used.
Great question. So the question is, to what extent can maybe these libraries also help each other, enrich each other, and not only exist as two choices at runtime? I haven't really explored that yet. So far, I'm only at the point of, you can try one. If it fails, try the other. I think what I would at least want to do is kind of automate that process. So that the software tries the first one, and if that crashes or produces bad results, automatically try the second one. As a next step, I would envision that I'm able to rewrite the results from one library to the other. And by that time, you would maybe use, indeed, a more intelligent combination of the two. Like this Minkowski sum that I showed, make an element a little bit larger. It also relies on convex decomposition, that you decompose your element into convex parts. That is really quite powerful and something that I think only CGAL offers. And if you can bring that maybe to OpenCASCADE for some reason, I don't have a very good use case in mind, I think that would be quite powerful. But so far, no plans. It's a quite slow process. But thanks for the question. Yeah, please.
I had a question regarding the open spaces that you have between walls for deletation. Is there a class for defining the deletation? Because then the next thing will be that you interpret it in a different way. You can either close it or put a flexible material in it for strength calculations.
Interesting question. So the question is, I mentioned earlier that walls are not always connected to account for dilatation, that elements can grow and shrink a bit. And is there a specific class to encode that information in the models so that can also be handled? I would say yes and no. If you would want to, I would say the standard is flexible enough to encode that information. The standard is also various parts, so there's a geometry description, there is a taxonomy of types of elements, and you can also refer to other classifications. So if you want, you can encode that information. The problem with that is also that IFC is used to exchange information from one person to the other, and there's a lot of inherent knowledge that we all rely on. So, if two walls don't exactly match, there is probably some textual description there that still says, well, this needs to be sealed with that and that. And that's obviously also much more efficient.
Difficult to interpret for a computer.
Yeah, but people in our industry, I have to admit, don't really care about that. It is a machine interpretable standard, but people still use it predominantly only for communication and
information.
And coordination. So you can, let's say, superimpose the geometries, and if there is a beam going through a wall where there is no hole, you have to call each other and solve that. But actual computational analysis on these models is still rather rare.
Yeah. Thank you.
Thanks. Yeah? Two? There is a microphone on its way.
Hello. When we say about IFC, we should remember about the versions of IFC. What is about the versioning with your libraries and all this stuff, and how you are related to all these things? I mean, the versions of the standard, because it's also going on.
Yeah, and it's actually also one of the reasons why I had to create this mapping layer, because I didn't discuss it, but we indeed, for example here, IFC 2x3 and IFC 4, we have more or less the same concept. There are minor differences. But I haven't really found a way, for example, to account for the fact that these two classes, the polyline in 2x3 and the polyline in IFC 4, that they are, let's say, 99% compatible. So it also really dramatically increases the compiled size of my platform, because everything is compiled multiple times with slight variations to account for the for the different schema versions. And yeah, there's other software libraries that maybe more start from above, have a unified schema, and then allow to serialize that as version 2x3 or version 4. But I have them more side by side as really computer-generated code from the schema. So yeah, we have migration scripts to go from the one to the other, but they are written by hand and probably not complete.
Okay, one last question, and then we're going to change over. Okay.
So let's change over one.
Lucas is going to unblock. So go ahead.
So your voxelization code, how did you set the voxel size? Because I assume if you set them too small, you don't find the holes in the wall, and if you set them too big, you close up corridors. So do you have to do an optimization for the size of the voxel? And what sort of size are we talking about for a building?
Yeah, a great question. And the main consideration was actually performance and also memory usage, because it's really a cubic relationship. If you halve the size of your voxels, your memory usage increases 8-fold. So, but the good thing about the construction sector, as opposed to, let's say, general purpose CAD, is, well, it all relates to us human bodies. So we're pretty sure about, let's say, the size of the geometries we're going to expect. And yeah, for that kind of reason, I also didn't create an optimization step to find the optimal voxel size, mostly just 5 centimeters.
Okay, so thank you very, very much. We're going, and that was excellent.